So, oops, that's not what I want to do. And actually, I'll make sure that I'll show you this section. Under the Files tab, I put up these T tables, which we'll kind of be using today. So just like the Z tables moving forward, I'll kind of expect you can either have these digitally or print them out and bring them to class with you. We'll go over this a little bit today. I also put up practice materials for the next exam, which is going to be 2 weeks from today. Okay, so 2 weeks, I'll put an announcement on my Canvas that mentions all this. But 2 weeks from today, we'll have a next in-class exam. We'll finish confidence intervals today. And then next week, I'm not going to be here. So what I'm going to do is put up a replacement video for what we would be covering next week, which is hypothesis testing. Right? So I try to be very deliberate in recording this video. And my suggestion would be as you kind of work through it, or listen to it, stop at points to try to, trying to clarify. Don't let it just continuously run. If you get lost, right, maybe pause it and try to figure out what's going on there before you hit play again. It's only about an hour and a half, but like I said, I tried to be kind of deliberate in what I did. So basically, hypothesis testing, we're going to have, I'm going to interview, I'll talk about that subject in those videos. And it's going to be for the same 3 types of examples that we've done confidence intervals for. So the confidence intervals, we already went over situations where we have a sample mean and a known population variance. We're going to look at confidence intervals already for a proportion. And then today we're going to do it for sample means when it's more practical when we only have a sample variance. Okay. So because I won't be here, I'm also going to extend the due date on the Excel assignment to that Wednesday following, like with the class right before our exam. I hope that you don't wait to do it until that Wednesday. After today, you'll have everything you need to complete it. So I work on it next week. If you have questions next week on it, I will be available via email, and potentially even could set up a Zoom meeting at certain times. But that's kind of where we're going into the next 2 weeks. Any questions for me on that? Yeah.
So you're going to be gone all next week or just one day?
So I'll be gone every class next week. All right. So we won't have class next week. I'll put up these replacement videos. So I guess have to get out a little bit. But like I said, I'm expecting once we come back that you've watched that video, right? I think I said videos. I was going to make it 2. I ended up just putting it all into one file, so it's all right in the same place. What I might do is kind of play the first third, maybe take a break. Don't have to listen all to it continuously. Then do the next third. It should be kind of in thirds, right? So the first third will be I'm talking through hypothesis testing for sample means where we know the population variance. Next third, I talk about hypothesis testing for proportions. Next third, I talk about hypothesis testing for examples like we'll do today, where we only have a sample variance and a sample mean. Okay. Now, once we come back that week we have the exam, that Monday and Wednesday, I'll basically expect you to watch that whole video, and I'll probably go through more hypothesis testing problems, just hypothesis testing on that Monday. We'll probably do just more general overall review. So we'll do some hypothesis testing, some confidence interval stuff on that Wednesday, kind of getting us prepared for that exam on Friday. Okay. Any other questions on that? And I'll put an announcement up on Canvas that mentions all this when the next exam date is. Kind of where I'll put a link to the video up on YouTube. Other than that, there's no question. We'll try and jump into material here for today. Okay. So, where did we leave off? We were looking at confidence intervals and doing these for proportions and for sample means where we knew the population variance in Excel, right? And there we were using that standard normal or the Z table. So our student T distributions, right? Or sorry, I'm jumping the gun. What? Here, we'll write down what we had last class. So we had this for comparison. This is how we're finding our confidence intervals, right? We're building them around our sample mean, going a certain number of standard deviations to the left and the right. And if that's the number of standard deviations where I need to go, well, I need to multiply that by whatever the standard deviation of our sample means actually is. Okay. So if instead I don't have this known population variance, which is probably more likely to be the case, so I don't know the population mean, I probably don't know the population variance. All we're going to do is replace that population variance with a sample variance, right? I mean, once I plug the numbers in here, nothing looks different, right? And I just use slightly different notation because now I'm calculating the standard deviation of my sample means using a sample variance instead of a known population variance. But the process is going to be exactly the same. There's also going to be something else, that changes, which is not only do I calculate the standard deviation with a sample variance now, but I'm no longer going to be able to use these standard normal distribution. We're going to have to use something that we call kind of the student t distributions, right? It's a family of distributions, and we're going to have to use those instead of the z tables or the standard normal, right? And I'll kind of give you some intuitions by why in just a second. So we don't have one student t distribution. We have one set of t tables, right? But every single sample size has a different student t distribution, right? So when we're using our sample variance, if we were trying to do things like, sorry. If we were trying to like convert sample means into t values here, the problem is typically if you subtract the mean, divide by the standard deviation, you end up with a z value. When we only have the sample variance, because we calculate the sample variance by dividing by n-1 instead of n, it's going to always overinflate our variance a little bit, making our distribution not a standard normal or z values, but it's going to be a student t distribution, right? So it's going to be very close to a standard normal, but it's a little bit more spread out, right? Because think about this, if I divide by 4 instead of 5, dividing by a smaller number, that creates a higher variance, right? So I have these slightly more spread out distributions, but as my sample size gets higher and higher, right, this actually gets closer and closer to be an approximation for the standard normal. So if I had, 1,000 as my sample size, well, divided by 999 instead of 1,000, that doesn't change the variance very much. And so it's not much more spread out than the standard normal, or it'd be a very close approximation. In fact, I think, did I have it here? There it is. Step or problem 3 here, there's 0.3. Once I get past 100 sample size, I'm probably okay, right? I'm probably okay to use the standard normal. It'd be a very close approximation. Okay? Now it's still symmetric, so it's still centered around 0. So just like our z values, it is normally distributed, and it does have a mean of 0. But the difference is our z values, those were normally distributed, mean 0, variance 1. Our t values are normally distributed, mean 0, but a variance slightly larger than 1. Right? So the larger, it's the only real difference between our student t and our standard normal is that variance is a little bit greater than 1. Any questions on anything up to this point? Okay, so show you kind of on this. I think this is a good slide here. So I've got 3 different distributions here. I've got my standard normal, it's that black line. I've got a student t when I've got a really low, what we call degrees of freedom. So all my degrees of freedom is my sample size minus 1, right? So it kind of accounts for the fact that I'm dividing by n-1 instead of n. I think I might have had this. Did I have this on an earlier slide? There it is. Sorry, I skipped over an accident. Our degrees of freedom, it's really just scaling the sample size, just sample size of -1. It's that easy. Okay. So if I had 2 different distributions, one that has degrees of freedom of 5, the other that has degrees of freedom of 20, right? As I'm getting a larger sample size or a larger degrees of freedom, my distribution is getting a lower variance, right? So it's becoming more peaked up until, it's kind of getting closer and closer to that standard normal. Now, once I get past 100, we said like it'll almost be indistinguishable from the standard normal, but it still will be slightly different, right? But yeah, if I got really large sample sizes, my student t distribution I'm using is going to be very, very similar to a standard. But for these lower degrees of freedom, it could be a lot different. Now, remember what we were doing when we were building confidence intervals before. So if I have this z value, I believe this is the value I use on the slide here. If I wanted 0.025 in the upper right tail, I think the z value that gives us that is 1.96. So the problem is, if I have a distribution that's more spread out, and I'm really going to like exaggerate this here. All right, so this is like my degrees of freedom of 5, and that's my student t distribution now. Well, now notice if I keep using the same value of 1.96, well, I'm no longer going to have half of alpha 0.025 in the tail. I'm going to have a much larger probability, right? So I can't keep using the same values I was for my standard normal distribution as I am for my student t, right? So when I'm trying to figure out how many standard deviations away do I need to go to get alpha over 2 in the tail, that value is going to be different when I'm looking for that same alpha over 2 in the tail area, but from a student t distribution. I'm going to have to usually go a higher number of standard deviations away to build my upper and lower bound. So this one I kind of have, you can kind of imagine these like 1.96, the area under my standard normal and black curve, very small. Once I look at these other degrees of freedom with student t, I'm going to have a higher probability. It's not going to be that desired alpha over 2. It's going to be something much larger. In fact, if I actually look these up, it's what, 0.062 and 0.068. So, quite a bit off of that desired alpha over 2 in the tail. My confidence interval isn't going to correspond to that correct alpha. Right? So we have, instead of a standard normal table, we have this thing called the t-tables, right? So this is kind of a truncated version of it. I think I'm just going to pull up the one that I put up on Canvas and also have the z-table so I can kind of relate the two. So here is my student t-table. So first I'll talk about how it's a little bit different than my standard normal, and then I'll talk about how it's similar, okay? So the difference is that it no longer is looking at the left side of the distribution, it's actually looking at the area in the upper right tail. Now that shouldn't matter for us, because if we think about, what do I want to erase right? So if I think about this, if I've got, let's say I got a degrees of freedom of 5. So the way that I'll read this table, I've got my degrees of freedom as my rows, right? The area in that upper right tail, that's represented in my column headings, right? So even though this says alpha, it might be good if you print this out, just scratch that out because it doesn't correspond to the alpha that we'll be using in our confidence intervals. All alpha means on this student t table, it's just the area in that one tail. So if I know the area in this one tail is 0.05 at a degrees of freedom of 5, the value that should give that to me is 2.015, right? So that's how I kind of read this table, right? I know the area I want in the tail, so I find the column heading that corresponds to that. I then go down to my degrees of freedom. Here, if my degrees of freedom was 5, the t value that gives me that area of 0.05 in the tail, positive 2.015. Now, there's no left side of the distribution here. There's no negative values, but it doesn't matter because if it's symmetric, if I wanted 0.05 in my lower left tail, what value is that going to be? So if there's 0.05 to the right of 2.015, 0.05 would be the area to the left of that same value, but negative. Remember, still centered at 0. Right? So if I know the area to the right of the positive value, I know the area to the left of that negative value. Okay? So it doesn't matter that we only have the right side of the distribution here. And because it's symmetric, we can kind of, look up those values. Yeah, the area to the right of the positive value is going to be the exact same as the area to the left of the negative value. Okay? So this table is similar to what we were doing with z-tables because at different degrees of freedoms, I can look up the area I want in the tail and find corresponding t value. Or I could look up a certain t value and find the corresponding area in the tail. That's exactly what we were doing with the standard normal. It's just that the way it's displayed, when we had the standard normal distribution, our z values were the row and column headings, and then our area in the tail or the probabilities were these numbers in the middle. Right? But we're still doing the same process, right? I could look up the z value of negative 3.56, find the area to the left of that, find the area in the tail. I could look up an area in the tail of 0.002 and find the corresponding z value, right? We worked in both directions there. I can do the same thing with my student t. It's just that now the probability or the area in the tail, that's my column headings. And then before we had our z values on the outside, like a row and column. Now our t values are going to be the numbers that are in the middle. But we can still use the same process. I can look up a t value, find the corresponding area in the tail. Look up an area in the tail, find the corresponding t value. Okay? So we're really using it the same way. It's just that it's a little bit different because our t values are in the middle now, and we only have 6 columns for the area in the tail. So it's a little bit harder to use the student t outside of using like Excel because we're kind of limited to really only these 6 areas in the tail, but that's okay. Because when we're doing things like confidence interval and eventually hypothesis testing, what are our benchmarks? We said last class, I'm looking at different confidence levels. Typically it's like 90, 95, 99. So my alphas are always going to be 0.1, 0.05, and 0.01. Half of alpha is always going to be 0.05, 0.025, 0.005. If I'm using these same 3 benchmarks, those values are going to be the ones that I can find in that student T table. All right, so if I ever wanted to build a weird confidence interval, I've got a problem. Like if I wanted to build a 96.3%, well, then this table is going to be somewhat limited. We have to go to Excel to kind of see how we can do that. Okay. Let's think if there's anything else I want to say here about the table before we keep moving. Any questions up to this point? We'll work through some confidence interval examples here with some actual numbers. Yeah.
Where is it supposed to be the square root of x to minus 1 or square root of x?
Oh. Yeah, so that's a good question. When I'm calculating my standard deviation of my sample means, I still just divide by my sample size. The only thing that my degrees of freedom is used for, it's not used in any calculation. All it's used for is to identify which student T distribution I'm using, right? And basically, it's identifying the function would change a little bit for different sample sizes, so you'd be integrating a slightly different function when you're looking for the area under the curve. So it's not involved in any of the calculations, it's just involved in identifying which student T distribution you need to use. Does that make sense or answer the question? Okay. Other questions for you? So I want to point one thing out. I mentioned that as I get a higher sample size or a higher degrees of freedom, the student T distribution should be getting closer and closer to my standard normal. So notice at very low degrees of freedom, my T values here are pretty high to get the same area of 0.05 in my tail. As my degrees of freedom goes up, notice that value is getting smaller and smaller. I need to go fewer standard deviations away to get my upper and lower bound. If I go all the way down to the very last column, the student T table here kind of has a nice like little cheat code where these are actually this last row. If I had degrees of freedom of infinity, well, dividing by infinity and infinity minus 1, it's kind of this weird theoretical thing that like it's the same math. So once I get to degrees of freedom of infinity, I'll actually have my standard normal distribution. So this last row tells you the values you would have needed to use, the number of standard deviations the way you need to go, get that area in the tail from a standard normal, right? That last row is kind of like our standard normal benchmark. Notice it's the same values that we've been finding using the standard normal, but a little more precise. So instead of 1.6, in between 1.64 and 1.65, 1.645. Instead of being in between 1.28, 1.29, 1.282. Instead of being, actually, here we've got exactly 1.96, so that one works out to be the same. Right? Instead of 2.33, it's in between 2.32 and 2.33, 2.326. So we can be a little bit more precise using this last row, right? And that's helpful for things like confidence intervals and hypothesis testing, because the areas that are in the tail, those are the ones that we typically look up, right? We're not going to have any weird ones. Does that make sense? And notice, as the degrees of freedom gets larger, that T value is getting closer and closer to what that standard normal value would be. In fact, once you get to 1,000, you almost, it's almost indistinguishable out to the third decimal. Just to the first decimal, really anything past 100, we're within about 1 decimal place. So we can kind of use that standard normal as approximate to approximate if we had these really large sample sizes. All right, so that's our student T table. I kind of mentioned that last row is our Z values. So we've got everything we need here. I'm going to consolidate all this before we start to work on a problem, okay? So let's say, thinking about the steps for our confidence interval, it's the exact same steps as what we were doing before. It's just that now we're going to be using that student T distribution. Okay. And what's in parentheses here, this isn't like multiplied by this. This is just saying it's the T value that corresponds to having alpha over 2 in each tail at the degrees of freedom of n minus 1. Okay. So I'll write this up here. and we want to calculate the intermediate step. So what we could do is do this all at one time. I think that that's not as easy, but just to kind of show you what that would look like. All right, I could substitute that formula in, do this all at one time. Just the way that I generally teach it and the way I would generally approach it. I'm just going to calculate this ahead of time. That way I only have one value to plug in. Right? I just think that makes it a little bit easier not to make a mistake. So we've got our same steps basically as what we were doing before. It's just now we're using that student t distribution. Okay. So let's work through a problem and try to kind of see how hopefully it's very similar to what we were doing before. So I take a sample, and this doesn't really have a context. So this is just going to be getting our first example is just using some numbers, right? Then I'll have some stuff that makes it a little bit more practical we could actually use. So I've got my sample size, my total 36 observations. I also have a sample variance of 324. Okay. So I've got, some sample, I don't know the population variance, so I had to calculate the sample variance. I've really noticed I've got everything I need here. I mean, I can do the intermediate calculation, which is find the standard deviation of my sample means. That's just the sample variance over my sample size. I think if I do this, I think this is 3, and check me to the phone. The sample mean we already had was 9. The only thing I have to do to build this confidence with what's left is figure out what t value I need that would give me alpha total outside of that range. So the total area in my tail would be alpha. That means I've got half of alpha in each tail, right? Well, what alpha value do I want? I think I'm going to cheat here, but I just give you alpha, right? So 0.01. So 0.01 is my alpha value, which means half of alpha is 0.005. If my alpha is 0.01, what confidence interval does that correspond to, or what confidence level? Now, 0.01, 99%, right? 0.01 is the decimal form of what's outside my interval, so it would be 1% outside. What would be within my interval? 99%. So I've got the 99% confidence interval that I'm trying to build. The next step is I got to look up, the only other thing we said we needed is that t value. Well, what's my degrees of freedom here? We said that's simply n minus 1. So 36 minus 1 is 35. Okay. So I'm looking for the t value, or the number of standard deviations where I need to go, at degrees of freedom of 35 to get 0.005 in each tail. So I'm going to go up here. 0.005 is the area I want in the tail, right, in each tail. I then scroll down. 35 was my degrees of freedom. So the t value that gives me that desired area of 0.005 in the tail is going to be what? 2.724. I'll add my margin of error, or go that many standard deviations above to get my upper bound. I'll subtract my margin of error, or go that number of standard deviations below to get my lower bound. Now it's just a matter of plugging that into my calculator. Right, I've got 3 values plugged in. Right now, I have got 2.724. Got everything I need to compute that upper and lower bound. So, what does that look like? There we go. Something like this. Right? So we identified the information that we were given. That's everything that we should need to build a confidence interval, other than figuring out how many standard deviations away we need to go, using that t table now. Calculate the intermediate step, but I think it's easier to just plug in one value. Now I could have done it all at once. This is another way of writing this out. Remember I said another way that we sometimes can write this mathematically, because the square root of anything is itself. Could have also used that form. Just depends on the problem and what information you're given. So plug everything in, right? Hopefully this is, I'm only dealing with 3 numbers. It should be a little bit easier, right? If I did the intermediate stuff. So I get a pretty wide range here, right? It's not the most useful, right? I mean, I guess with 99% confidence, whatever variable this is, I can say it's positive, right? It's all the only values are positive, but it's a pretty wide range. Right? Any questions about anything there? How I looked up the t-value, or want to hear something again? Okay with that? All right, so I've got another example that has a little bit more context. That might be a little bit more interesting. So I've got the exact same kind of setup here. Just now I'm looking at the AMA saying, okay, the average starting or average mean salary, or the mean salary for positions is 179,000. I take my own sample of 81. So I'm just going to start writing out what they're telling me. N is 81. I found a sample mean of 160,000 and a variance of 324 million. So that's everything I was given. If I wanted to build what confidence level? If alpha is 0.05. Yeah, 95% confidence interval. What would it be? Well, here I can calculate that intermediate step, taking the square root of 324 million over 81 people. I think, if I'm remembering correctly, this is about 2,000. So I've got the intermediate step calculated, so I can just plug one value in. I know that my sample mean is 160,000. The only thing left I need to do is figure out how many standard deviations above and below do I need to get alpha total outside of my interval, or half of alpha on each side. Right? Well, what's my alpha value? 0.05 over 2. So the area that I want in the tail is 0.025. What's the other thing I need if I'm using my student t distribution, because I only have a sample variance? My degrees of freedom. So 81 minus 1. I've got degrees of freedom of 80. Okay. So I'm going to look up on that t-table at degrees of freedom of 80, the area I want in the tail, which is half of alpha, or 0.025. Okay. So I go here, t-table. I want the area of 0.025. So I'm in this column. I then scroll down to the degrees of freedom of 80. The value I need to use is going to be 1.99. Okay. Now that I've got that, that was the last thing that I needed. It's got three values there. This value minus this value times this value. Okay. Any questions about how I found that t-value? So you're using that degrees of freedom, and that area you want in the tail are half of alpha. Okay. Now, before we kind of go, I want to point something out. The same principles apply to what we were doing before. So in this one, for instance, 160,000 is my sample mean. It should be smack dab in the middle of my confidence. If I'm looking at these, answer C, 160,000 is a lot closer to 163 than it is to 146. All right. So I could actually rule C out because 160,000 isn't smack dab in the middle. Now, the other three are all possible. So from there, I just have to actually do the work. All right. But I could rule answers out if my sample mean is not exactly in the middle of it. Okay. So if we go through, we've found that t-value at the degrees of freedom of 80. We calculated the intermediate step, which was the standard deviation of my sample means. Now it's just a matter of plugging those three values in here, subtract to get my lower bound, add the margin of error to get my upper bound, and I get a little bit more of a narrow range. So with 95% confidence, I can say that the true mean salary is somewhere between 164,000 almost to 156. Right? So the AMA is saying that the true mean salary is 175,000 with 95% confidence. What can I do? I can tell them that they are wrong, right? 175,000 is not one of the values I have in my range for what the true population mean is. Right? Well, I can tell them based off the sample I took that they're wrong, right? That the 81 positions I found, right, building a confidence interval around that sample mean, the only possible values for the true population mean are in between 164 and 156,000. Right? So I could tell them they're wrong, right? 175,000 can't be the true mean. This seems kind of stupid for like examples with salary, but we've talked before, if I want to know the amount of medication in a drug or, weight of the drug or something like that, like this is a lot more more important. Couple other things I want to point out, and then I'm going to show you a little bit of stuff in Excel. What happens when I want to say things with higher levels of confidence? So, I could reject the AMA's statement. I could tell them they're wrong at, the 95% level. But would my confidence interval include 175 if I went to the 99% level? Well, if I go to the 99% level, what's going to happen to alpha? Alpha is going to get, I go from 95 to 99. Alpha is getting smaller, right? So alpha over 2 would be smaller. If I want a smaller error in the tail, what's going to be true about my t-value or the number of standard deviations away I need to go? I'm going to have to go a higher number of standard deviations away or use a higher t-value. If my t-value goes up at this higher level of confidence, I'm adding and subtracting a larger margin of error, I'm going to be getting a wider range of values. So if I want to say things with high levels of confidence, I'm going to be getting a wider confidence interval. How wide does it get? I'd have to actually go through the calculations, but possibly at a 99% level, maybe the confidence interval does go past 175,000 on the upper bound. I don't think it does. I'm not sure that the numbers play out that way, but it's a possibility. Right? Well, what can I do if I want to say things with a high level of confidence and I don't want to have these really wide intervals? We said, if I make sure that I've got really high sample sizes, what's going to happen to my standard deviation on my sample means? The denominator is getting larger here. This value should be going down. Right? If this value is going down, I'm adding, subtracting a smaller amount, I'm getting a much narrower range of values. So even if I want to say things with a high level of confidence, if I take really large sample sizes, I can still kind of narrow down where that true mean is, right? Like I said, maybe it's not as important I nail down the true mean salary of a physician, but nailing down the true weight, average weight I'm seeing in this medication might be really important, right? Or whatever the example is. So I'm also going to go through and show you how we do this in Excel. It's very similar to what we did on Wednesday, and I'll also kind of I can kind of do some work on the board to kind of match up with Excel so we can see what's happening. So, get rid of this here real quick. The board space. So this was what? Making sure that we can still have this. All right. So last class, and I put this up before class today, or I didn't put up, well, I'll do it right now. Let me see. Let's go back to files, in class data. I'll put up the one that we were using last class that has our work so that everybody, if they want to, can kind of follow along. Actually, it's at the top here. So I've got, this was ours. Okay. So the YouTube in class one, that's the one that I'll be using. So we'll pull this open. So we have our work from last class. What we're going to do is I'm first just going to copy this table and paste it over here. Okay. I'm then going to go over, delete this. That's, oops, I hit backspace, not delete. But that's just so I don't have to type this all out again. If you really wanted to, you could type it all out. What we're now going to do is say, look, I don't have this known population standard deviation or known population variance anymore. So let's assume I didn't know that population variance and all I could find was my sample variance. So in practice, like this isn't going to be the case, but I'm just using the same data so I can kind of compare and contrast. If I know the standard deviation, population standard deviation, how does that look different from if I only had a sample standard deviation or a sample variance? Okay. So how do we find the sample variance of a variable in Excel? Well, that was just var.s, right? We go over, I think it was the likes variable that we were looking at. So I'm going to hold Control Shift, hit the down arrow, hit Enter, and I've got my sample variance, pretty large, right? We then had our sample size and our sample mean over here. So just so I don't have to scroll, I'm going to, oops, I didn't want to do that. Just wanted to paste the values. I'm going to copy and paste those values just over here. So one kind of nice trick in Excel, if I copy, when I go to paste, if I just want the values, there should be another option there. So I can just paste those values. Or if I didn't want to be lazy, I guess technically I could have just copied and pasted the labels and said, here's my sample mean, here's my sample size, right? However I want to do it, I'm just trying to get it so that I don't have to keep scrolling over. So what's going to be different, right? Well, the notation changes, but really all we're doing is using the sample variance instead of the sample standard deviation. And then on top of that, we can't use the Z table, or we can't look up Z values anymore. Now we're going to we need to look up a T value that gives us alpha over 2 on each tail. So last class, how were we finding the Z value? Well, when I know the area in the tail and I want to find the corresponding Z value, we're doing the inverse, right? So we use norm.s.I and V. Now, if I only have a sample variance, I know I have to use the student T distributions, but I'm still wanting to do the same thing. I know the area I want in the tail, and I'm just trying to find the T value that corresponds to having half of alpha in each tail. Right? So instead of norm.s.I and V, T.I and V, right? Instead of using the standard normal, instead of norm.s, we're using student T distributions. That's it. So T.I and V. We'll still tell it the area we want in the tail or the probability in that lower left tail, which is alpha divided by 2, right? That's the area we wanted in each tail. The other thing that it now needs that the norm.s.I and V function didn't is we need to tell it our degrees of freedom, right? Our degrees of freedom is simply going to be our sample size minus 1. So the first thing I tell it is the area I want in the tail, or half of alpha. The next thing I tell it is my degrees of freedom, which I know my degrees of freedom is simply n minus 1, or my sample size minus 1 there. Okay. Any questions on that? I mean, if you technically wanted to, you could have calculated the degrees of freedom in another cell and then just selected that value, but you could have just done n minus 1 here. Now, if I copy this down, what's going to be the problem, right? So I'm building 3 different confidence levels for this sample evidence, right? So the same sample mean, but I'm building 3 different confidence intervals. Well, I want alpha to change for the different levels of confidence, but I want to keep using the exact same sample size, right? That's not changing at all. So I'm going to go in and make sure that I freeze that sample size cell reference. And now it's only allowing that kind of alpha to update. So I'm getting my T value for these 3 different levels of alpha. Okay. Any questions on that before we keep moving here? Yeah.
Does that need to be an absolute value?
Yeah, so you're jumping the gun on me. But yeah, if I hit enter here, what do I know is going to be true? If I'm looking up alpha over 2 in the left tail, I'm always getting the negative T value. We said in our confidence interval equation, that's kind of already built in, right? We're subtracting, we're going that many standard deviations below to get our lower bound. We're adding or going that many standard deviations above to get our upper bound. So what was a really quick, easy fix we had for that? Just using that absolute value function. Yep. That should just give us the same value, but positive. Okay. So from here, the only thing left I need, I've got my sample mean, I've got my T value. I need to figure out the standard deviation of my sample means. So, and actually, I'm going to put this over somewhere else. Oops. So all that's going to be is the square root, right, of my sample variance divided by my sample size. Right? You don't have to just, you could make this equation, plug this formula in and type this all out in one cell if you wanted to. I just think this helps make a lot easier, right? So I calculate this ahead of time. I'll have my standard deviation of my sample means. So now when I'm building my lower bound, well, that's just take my sample mean, subtract this many standard deviations, right? That's the T value that I'm using. And then multiply that by whatever the standard deviation of my sample means was. I mean, it's the exact same setup as what we did Wednesday. It's just I'm using a T value instead of a Z value. Okay? So when I copy this down to the next 2, what's the only thing that should be changing? Still got the same sample mean. That's not changing. I'm building confidence intervals at different confidence levels. The only thing changing is my T value or my alpha. Okay? So that's the only thing that I'm gonna want to change. So I'm gonna freeze the cell reference. Oh, I messed up. I'm gonna freeze the cell reference for the sample mean and for the standard deviation of my sample means. Now, when I copy this down, it'll only update that t-value, which is what I wanted to do. Now, my upper bound equation is going to be this exact same thing, except for what's the only thing that's going to change? Yeah, I add my margin of error. So what I think is kind of a nice, easy shortcut, if I am in the cell and I copy that formula, hit enter, go over here, paste it, it won't change any of my cell references, right? Which is great because I wanted the exact same cell references for my upper bound. The only difference was instead of subtracting my margin of error, I wanted to add it, right? So copy and paste that formula. Then it's just a matter of changing that negative to a positive sign. Now I've got my upper and lower bound. Any questions on that? Okay. So now, if I've got everything set up correctly, I think I've got everything frozen correctly. I can just copy this down. I've got my 3 confidence levels. Notice, as I'm saying things with a higher level of confidence, what should happen? My intervals should be getting wider. Sure enough, my lower bound is getting lower, my upper bound is getting higher. Any questions on that? Want to see a cell again, or? Yeah.
I see the SPS sample needs.
Yeah. Yeah, so all we're doing there is just taking the square root of wherever our sample variance is, divided by our sample size. Yep. And like I said, if you really wanted to, instead of like adding in that reference, you could have went like times the square root of the sample variance over the sample size. So you can do it all in one cell. The number didn't change at all. It's just, I think it's easier to break it down into parts. It's easier to make, it's less, it's harder to make mistakes, I think, if you break it down into parts. Any questions? Or keep moving here. Question. Okay. So, just a couple things to point out here. I've got a huge sample size, right? So what should be true about the t-value I find relative to if I did have a standard normal distribution? Well, notice they're very, very similar, right? 1.64485 and 1.64489. So I'm only off at like the 5th decimal, right? So when I get these really large sample sizes, we said we could use a standard normal and it'd be a very close approximation, right? But what I want to highlight is, let's say instead of 37,000, let's say I only had 30 as my sample size. Well, what's going to happen if I have a sample size of 30? That means that I'm going to have a much more spread out student t-distribution, which means the number of standard deviations of the way I need to go to the left and the right are going to be quite a bit different than the standard normal values. So if I hit enter here, sure enough, instead of 1.6448, we're at 1.699, right? So it's quite a bit. I need to go, 0.05 higher standard deviations to get that desired alpha over 2 or the desired confidence level I want. Right? So with lower sample sizes, it's a lot more important that we know how to use the student t-distribution. Once they get really, really large, well, it's very, very close approximation if I accidentally use the standard normal anyways. Questions on that? So I pointed this out to the other class. So I will extend the due date on that homework, like I said, to be that Wednesday before our exam. So you have all of next week and then half of that following week. You should have been able to already do part 1. That's just a normally distributed variable. 2A, that's going to be exactly what we did on Wednesday over here, right? Where we have a known population standard deviation or a known population variance, and we're building a confidence intervals at the different levels. 2B, you're looking at the proportion of CEOs who are male. So you're not looking at their salary, you're just looking at the proportion. So there's a 1-0 variable in there for whether or not the CEO is male or not. That's what you should be using here. That should line up with what we were doing for that more likes than dislikes variable, right? Which was also just a 1-0 variable. 3A and 3B are going to look identical to what we did here today when we only had a sample variance and we were comparing sample means. Okay. And then 3C asks, I think it was the example was like, did suicide rates go up? So I see a lot of confusion with this, or I have in the past when I asked similar questions. So if I build my confidence interval for 2018 suicide rates, and I build my confidence interval for 2022 suicide rates, or after these might be not quite the same years, but it's the same idea. If they overlap, well, what could be true is the true mean suicide rate in 2022 is here, and 2018 it was here, in which case 2018 was higher. It could be that 2018 was here, 2022 is here, which means 2022 rates are higher. So if there's ever overlap, I don't really know the relationship. I'm not simply comparing the means, right? Here, what is this centered around? Well, suicide rates, the mean was much higher in 2022 than 2018, but it's still just based off of a sample, right? So when I build this confidence interval and the confidence will overlap, I can't really make a definitive statement here, right? Now, if they don't overlap, so we kind of have the political examples that we were using when we were doing this before. Well, now, even that kind of worst case scenario, 2022 rates would be this low, 2018 rates would be this high, it would still be that 2022 is higher. So when they don't overlap, I can say that this other group has a higher mean, right? So kind of that part C, whatever confidence intervals you build in A and B for problem 3, you'll be kind of comparing those to see, do they overlap or do they not? Okay. Does that make sense? Are there any questions on this? Okay. So, something that is maybe, I think, a little interesting, and also relevant. So that should kind of do it for us for confidence intervals, right? So we've got 3 different types of confidence intervals. Sample mean, where we know the population variance, sample proportion, we can use the standard normal Z tables. When we only have a sample mean and a sample variance, that's where we have to use a student T. So we can build confidence levels for all 3 of those types of examples, and then those videos I'll be posting this afternoon, that'll kind of replace next week. Hypothesis testing for those exact same 3 examples. Okay. But what might be a little more interesting before we get out of here today, I was thinking about this, it's somewhat relevant. It's like this massive event that like there's something like 20 million brackets we're doing on ESPN and every, March Madness, a lot of revenue is generated around it. So there's kind of an interesting idea that we can use from this class, which is what's the probability of picking a perfect bracket? So even if you just think about the first round, there's 32 games. Let's just be very naive and say every game is a 50% chance one team wins, 50% chance the other team loses, right? That's naive, but let's just assume it. What would be the probability I get all 32 first round games correct? Well, the probability I get the first game correct is 0.5. Probability I get the second game correct is 0.5. They're all independent events. So if every single thing has a probability of 0.5, it would be 0.5 times 0.5 that many times, or 0.5 to the 32, which is like an astronomically low value, right? So that's the probability. I think I saw something today, like there was like 0.003% of brackets left that were perfect. For me to get every single game correct or to be perfect, this is what point is, after today, I bet this falls pretty close to 0.000000009 or whatever it is. Yeah, 2, sorry. Yeah. And you could complicate this and obviously there's more than 32 games, that's just the first round. So you would just then take 0.5 to however many games are played in the tournament, and that gives you the actual probability. But we know that every game's not equally as likely that each team wins. So like some games would be 80%, some games, 75 if we pick the favorite. So somebody did some work, and I have the value, so I'll just pull it up here down at the bottom. I think if you take that into account, it still ends up being a probability to get it all correct based off of the odds and these percentages. You'd still be like 1 over 128 billion, right? So if anybody does get a perfect bracket, I mean, it's essentially winning the lottery. Right? All right, I'll let you guys go. Have a fun, safe weekend. Feel free to reach out next week. I will be available via email. Like I said, maybe set up a Zoom if you need to. And then please, look for and watch those videos I'll get posted this afternoon. Oh, also, on your way out, since you all showed up, I want to give you kind of 10 for 10 on the day. Because it's a Friday, numbers were a little low. So everybody who showed up, I want to kind of give a benefit or